Woo! Around there. Let me switch over to this for a second. Now, we kind of did all that AI stuff I wanted to do. I've now got a proof of concept. The rest of what we were doing there needs to be sort of tweaked. I'm actually in the process now of working with Ed and Florin to rent a machine for a few days
Oh, okay.
to install this stuff and actually run it. I'm just waiting on Casey to give me the disk space requirements to download those videos.
Which is just all the file, like all
At
the.
least for one 20-hour session, right? So I want to download all the videos for Ultimate Service.
I feel like
I want them locally.
I feel like less than a terabyte would be enough.
Yeah, I was thinking maybe get like 5 terabytes of disk space.
I think
But
that
that has
holds
to be
everything.
I don't know. Florin is saying that we could leave it up in cloud storage, but see, this is the fun stuff, right? You build all this stuff on your machine, and now you got to put in production.
Yeah, that extra step, taking it away from like local hosts, you know,
Yeah,
like
no, I know. That's
that's
another
what.
level. So ideally, I don't want to pay for bandwidth to temporary copy files down just to use them for a few seconds. But at the same time, if we're trying to process everything over the internet, it could be really slow. Like, right? You might just whatever copy everything down. Maybe that takes a few hours, and you pay for that. But then everything processes really
Yeah, it
fast
just
because it's
moves.
locally, right? Like I've been in these situations.
Mm.
Anyway, I was going back through this list because we essentially, with the chat application, did this and did this,
Okay.
right?
Yep.
We didn't really do this, but we didn't need that. I don't want to do that.
Yeah.
This is something we talked about doing, number 6.
The file sharing.
Don't really need that. And that's a whole video class that I have already. That would have been nice to build online there, but I don't want to build that again. So when I come back through all of this, it seems like this might be, since we've got basically 3 shows before we get our lovable guy in.
Yep. Doing the file sharing.
It could be, but we'd have to get a full mental model of everything again. So what I thought we'd do, because we need to do this anyways, we do some programming.
Okay.
Let's build a little hack program to start where we implement, because when we were going to do file sharing, I said, let's just do it with HTTP, which would make a lot of sense, right? Just expose an endpoint and use the basic form upload sort of mechanics that already exist. Why rewrite the wheel? Which is another reason why I pulled back, because, that's not really a big deal. But what maybe we'll do is we'll go back to some low-level socket programming.
Okay.
And do a file transfer where we read the bytes. So we'll do some lower level stuff, but we'll just do it with a hack program, and then seeing how long that takes, that might be code that we can then integrate back into the chat system.
Okay.
Because remember, we have the peer-to-peer connection.
With the TCP.
We have the encryption, the decryption.
Yep.
We have all that. It's just a matter of writing the protocol to go across. And if everybody can hear Max crying, Max, why are you crying, dude? Come on, bro.
He's on fire today.
Man, dogs are all over the place today. I don't know what it is. I might have to just give him a snack. He knows when the show's on that it's like I can get a snack
right now.
Yeah, he just wants a snack. He knows the show's on, baby, and he just wants a snack. He knows they can get it. Dog. So I think that's what I want to do. Just build a hack program. We can transfer a file, and we're on the same network, so we can sort of, you can run it and I can run it, and we can do all that. And we remember how to even integrate all the networking stuff. So I've got the USDL project back up.
Yep.
And we already had a hack program in here that did what?
Dude,
this is the code we need, man. Okay.
TCP. I think that had pretty much like.
I needed the networking piece to do this, right? So, what was this?
TCP.
All right, let's read this code again real quick, because this was the part that was in my brain. I'm like, we gotta bring back the TCP package, and we gotta set up those types. So let's go see what this hack program was doing for us. Looks like we may have been writing this to deal with encryption. Let's see. So server side, we got a logger, we got a server config on port 3001. We constructed a new TCP server. So that means that's a server that can accept TCP connections.
Yep.
Then we're listening for connections, right?
Yep. And a go routine. Okay.
Okay. Then on the client side, we have this function we're going to look at that runs in a separate Go routine that probably establishes a connection to the server. And then we wait to sort of shut everything down by waiting for a control C. The sig term would be more of a production. Like we didn't need sig term in here.
Okay.
And then we can shut down the server side of things, right? So a very common pattern here. I have some global wait group. Remember that. Oh, it's the handlers that are everything, right? So we didn't implement any of the handlers here. Bind, drop, process, read. So we're going to have to do that. This is beautiful that we have this already, because I was already like, this is the code. I'm like, I got to remember how to put this code together. But we're kind of already here. Then, oh, we must have these implemented already. I just don't know where. We'll see these types in a second. So this is doing the connection. And then we've got our global wait group. I don't know why I made it global. And I'm adding 2. We're ranging over this, and we're connecting. Oh, we were just doing some basic send a string. Oh, dude, this code is perfect for what I want to do. We're gonna rewrite we're gonna do a lower level protocol.
Okay.
And then it's waiting. And I guess we weren't using this at all.
I see a bill.
So here's the server, here's the bind, here's the read, here's the process, and then here's the, oh, this is perfect, man.
That has NATs.
Well, I guess we had some NATs going on at some point in here too, but we don't need NATs for sure. At least for what I want to do. Don't need key. Don't need.
Oh, the PEM.
We must have been doing like coding in here.
There it is. Yeah.
Right, encryption. We can get rid of any noise that we don't need right now. What I really need are these functions here. I need these functions that we have to, or methods I have to implement, and these methods that we have to implement. I don't think we need this. For sure we don't need that. Okay, actually, this is a brilliant place to start from. I can't believe it, actually. So let me bring up a little whiteboard, and I'll tell you sort of what we want to do, because at the end of the day, what we really need to do is implement the server side of this,
okay,
and the client side of this. And ideally what we can do is we can say that the client connects to send a file to the other side. Remember, instead of trying to do like duplex things, you want to send a file, connect. We did that on the chat server, right? We had the two-way communication that way. Yeah. Just to keep it simple, right? Just to keep it simple, not as efficient as being able to say that one guy connects to the other and you don't need another connection on the other side. But let's just do some Excali draw, because this is stuff that we were playing with.
Man, it is coming down out there.
No, dude, we're having a storm.
And it's sunny too.
I know, but I swear some of it looks like, I guess now I'm looking at leaves. If I could turn the camera around, everybody would see the hurricane that we're getting right now outside.
Craziness.
And Max wants to go outside. Anyway.
Max being crazy.
I don't know if anybody enjoys all this is live, man. That's all I'm saying. I'm not trying to be professional. All right, look. Here's the idea, okay? Let me just say, we're going to have our client. We're going to have our server here, right? Somebody has to connect to somebody at some point. And there's just a line in between, okay? So these are our 2 client servers. And ideally what I want to do is say that the client is going to establish a connection to the server, right?
Okay.
So, right, establish a connection. That's fine. And we're going to establish that connection so we can, I liked how I could move it. Nice. I was able to move it before. Whatever. So we're going to establish this connection so we can send a file over, right?
Okay.
So let's talk about sort of the protocol that we want to implement here. Maybe I don't need the slide because it's bothering me. Okay, so we're going to establish a connection, but then what, right? I've established a socket connection.
Yep.
So in our little hack program, what would be nice, remember we had a handshake before because we wanted to know who that was. We don't have to necessarily do the handshake.
With the ping and the pong and
with the, hey, I'm your, this is my ID, this is all that. But for a little hack program, what we would do. So once we establish a connection, that's fine. We're going to know about that connection because on the server side, we're going to get this bind, right? That means that we've established a connection, and then we're going to necessarily be in a read. It's the same thing over here, right? We get the client bind, and then we're sort of waiting for a response to come back. Now, I think what we could do is once we got established the connection, what we could do is maybe send some metadata about the file. Would be nice to send some information, maybe the file name.
Okay.
It would be nice also to know what the size of the file is. That way it would be sort of interesting there, right? And then we could have a progress bar if you knew.
Oh, because you know,
what it is, right? But I think before you do that, right, we send some sort of ACK just to say I'm ready, right?
Okay.
So you've sent me this. I'm acknowledging that you want to do that. And then we've got to start sending the file. Now, this is TCP. So what we're going to want to do is send chunks of the file at a time.
Okay.
But the other side sort of needs to know how much data it's sort of getting, because this is going to be coming in piecemeal.
Okay.
So what we're going to need to do, I think, is the following. The easiest way to do this is sort of in 2 steps. Let me do this again. Sort of in 2 steps. So every time the client sends some data, it sends the length of what it's going to send in bytes.
Okay.
And then it sends that data. All right. So it's a length, but what's also nice, actually, if you do this, you're fine. Because sometimes in the early days, I would send like a marker, but you don't need that, right? Because once you do the ACK, you know you're going to get the length. And the length, let's say the most that we're going to send is 32,000 bytes, right? Like the number is going to be 32. How many bytes do we need to send the number 32? Probably 4 bytes, because it's, right? You don't need more than what is the max? Here's the question. What is the max 16-bit number? And we can use unsigned because we're not going to deal with negatives, right? So the maximum is that.
Okay.
So that's kind of cool because based on that, the length could be a 2-byte integer, right? So we can say that we're going to use 2 bytes. The first 2 bytes that come in will represent the length, and we can send up to then 65,000 bytes at a time.
Okay.
And then this will be whatever that length of bytes is. So for the first few packets, all right, let's say we use this, right? So for the first few packets, right, this number is going to say 65,000. And that's what we're going to send. Let's imagine that's 65,000 in length, right? And then you're going to send another 65,000. And that's going to be sent. The problem is that this is TCP. So this data has to be broken up into small packets. It's going to be delivered out of order, but that's what all those data layers are supposed to do. But by the time our function gets called, with some data,
Yep.
the chances of us having 65,000 bytes on that first read is slim to none.
Got it. Okay.
We might end up with, and we'll display this, right? Maybe we get 10,000 bytes on the first.
Sort of.
Maybe we get 4,000 bytes. Well, we know then that the next read we do is going to be what? Data bytes, data bytes, data bytes. Once we get that length, then we know the next byte is what? It's length information again. See what I'm saying? So by doing it like this, it will be really efficient. And then eventually this could be compressed data. So you can, but at some point, what's going to happen is this number is going to be less.
And that's how you know you're getting towards.
And that's how we know we got to the end.
Okay.
Because once, right? Something like that. Now, again, this is going to be happening actually more than we realize. Like we're going to send this. So we still need some way of knowing that we're 100% sort of done, right? We could maybe do that by sending sort of 0 bytes.
Like a final.
Yeah. So when the last 2 bytes represents sort of 0, then we know we're done. Because even though we're sending 60, right, we might first get, I don't know.
Yeah.
We're going to figure it out, number. Right? Like this is what's going to be coming down, whatever that is.
But
right?
the numbers would be within that 65,000.
Yeah, would never be larger than that. Well, technically, I'm wrong here for a second. Sorry. Hold on. These values are probably going to be 65,000 because that's how we're sending it from the other side.
Okay.
Okay. So we probably are going to get this length is always going to be some big number.
Yeah.
Right? The problem is that the data might come in chunks like this. As you're going to see, right? And until we get all of the data, we know that any packets coming in is data. And then eventually, we got all 65,000.
And then remove. Okay.
Now, if we did it this way, which is a fine place to start, then remember when we did the metadata file, what information could we put in here? Well, for sure, we want a file name.
File name and file size.
We want the file size. Now, if we do the file size, then we know we're done when we get all the bytes related to the file size.
Yeah, when it equals.
And if this connection drops before we get that, we could just say that we had a. Now, there's something else we can do after that. We could do a checksum. And that's going to be important. What the checksum is going to be is the client saying, here are all the bytes. I'm sending you a meg of bytes. And I've run those bytes through a SHA-256 or something. And here's the checksum. So after you get all the bytes, run it.
They should match.
If you don't get the same checksum, somebody's done something bad.
Oh, okay.
So as a tiny bit of sort of a security check to make sure there's nobody in the middle coming in and altering data, we could do like a checksum and validate that not only did you get all the bytes, you got all of the correct bytes.
Yeah, because if anything's changed, it'll change that sort of
checksum.
hash. Yeah.
Right? Yeah. So we're going to need eventually to do that.
And
then essentially when the total equals the file size, we should know that we're sort of done, and then we can sort of, everything can sort of drop.
When we're sending sort of the data there, are we deciding how that's broken up, or is it just
no? The network just the does
protocol,
that.
Like
so, we are going to ask the network. We're going to give the network 65,000 bytes at a time. Let's say, or let's say we do 32. Yeah. We do half of that, right? We're going to give it, and at the go level, we're going to say, here's a buffer of 32,000 or 65,000 bytes. Send it.
Okay.
Well, the network can't send that. It's going to be chunking it up at the IP TCP level, right? Or whatever those particular settings are for how you send data. And IP looks for different routes for efficiency. So packets come in out of order, but your network stack is supposed to put them all back together. And we're not going to get one big 65,000 read.
Yeah. It'll be
Right
a bunch of
now,
smaller.
thanks to the Go standard library, we have API calls that have you wait until that happens.
Mm.
The standard library has support to make it easy for you to say, hey, network read, here's a buffer. Don't return until it's
Until you
full
get it.
or
Yeah.
EOF.
Mhm.
But I want to code that ourselves.
Got it.
Okay. I want to go a little lower.
Yeah.
We wouldn't necessarily have to with Go. That's what the buff.io is, right?
Got it.
We could sit here and instead of saying read string, I'm sure there's a function here that would let you do read bytes. Okay.
Yeah.
And read bytes is what I want to code ourselves, which is fill this up and let's see what read bytes says. Bytes, right? Read bytes until the first occurrence of a delimiter in the input, returning the slice containing the data up to and including the delimiter. If read bytes encounters an error before. So this is interesting because they're looking for a delimiter, right? Read bytes reads until the first occurrence of a delimiter in the input. Now, I don't want to use the buff reader anyway, okay? And again, that's where scanners come in. Go has done all this stuff to sort of simplify. But
Yeah,
when I
so you
was
don't have to
coding
do
in
the low
C#,
level.
we have to deal with that. Bytes came in, and you had to sort of do that work. So we do have the concept of a network connection. We have a concept of the reader and the writer here. And I'm trying to remember if the connection has a standard read. Let's see what read does for a second. Reads data from the connection. Read can be made to timeout and return an error after a fixed time. See, I'm not sure of if read waits for that buffer to get full, will only read that many bytes out of the buffer. So we're going to have to play with it. Like I want to go raw here. I want to use the con as opposed to, say, using buff.io, which gives you all this sort of feature functionality already. Like, let's see if we can code some of this ourselves.
Yeah.
Just using a standard sort of read off of the connection, right?
Got it. Okay.
So what that would mean to me is we're not going to use any readers or writers on the bind. This is the server side. So on the server side, we're going to get a connection, right? The bind will show us that. Then we should get some metadata. Now, for the metadata, we have to remember if we can do that in the bind or not. Because if we go into the read already, then I have to know this is the first read as opposed to the sort of second read, right? So, and I don't remember how I coded all that. So if we go into TCP server, there's going to be a go routine. That's the listen. There's an accept. I bet you if I just look for the word bind. No, bind there. It's going to be in some reusable code, right? Like there's going to be a call to bind somewhere. That's funny that I'm only seeing it where in Nats and Nats. So now what I want to look for is an interface, right? That defined these interfaces that we were playing with here, right? So this is implementing an interface. So let's come back here for a second. This is implementing the handlers interface, right?
Okay. Yep.
That handlers interface under TCP. And you can see here that we've defined these sort of interfaces for the handlers, con interface. And that is, where is that file? Oh, tcp.go. Okay. Some basic like stuff here. But my guess is that when we do the listen, right? We have a go routine. This is all in the go routine, right?
Yep.
We start a listener, we accept. Anytime we accept a connection, we have this start new client. Boom, we had a new client. And I think the client we use, whether it's the server side or the other side, right? And there's the call to bind. Now, the problem is what I was, right? So this bind is holding. It's hold, right? So the bind has to return. And then once that returns, we add it, we can start. So I can't do anything in the bind because we won't have a go routine to coming back and doing reads and stuff. It's just too early. This is where sort of everything happens in here. All right, this is the read. And then on the read, we go ahead and we call read, and then we call process, read and process, read and process. So,
okay.
And the idea is read is getting the raw data. The idea is that, if we come back to our hack program for a second, is that read is returning the raw data, and process at that point lets you sort of process the raw bytes in our case, however you're doing it. That was the idea here. Like, get the raw bytes and then give it to process, which would be at a higher level of processing that data. Plus, you might have to come back into read several times to get all the data you need, which is what we're going to be dealing with.
Yeah.
So if you kind of look at this, it says wait for a message to arrive. This code is sitting here saying you block until you get all of the data. And so we're going to be here in read. If we're going to do this at a raw level, we're going to have to be this here in read, getting all the raw data out of the system.
Oh, okay. So we're going to be in that
So
sort
we're
of
gonna
read
right.
loop until we get that.
It's not
that-
even a loop. Yeah, we're going to loop in here until we get the full length of data,
Okay.
or we return an error. Then once we get the full length of data, then we can put it somewhere, right? Return it. So we have data here. A process, yes, gets this request, and then you have the data. So the idea would be here is get the full length of data that the length said,
Yep.
and then this can process that data. In other words, we can write it to disk or whatever it is we want to do.
Got it.
So we're going to be basically at a low level here, doing that, getting in the loop. Now, if I go back to our diagram, what we might want to do then is get rid of this ACK.
Okay. Why?
Because I think it's going to add complexity to everything. Since we're only focused on file server, what can happen then is in this read, this is what I'm trying to deal with. I need to get some metadata, right? And then I want all the raw data. And so my brain's trying to say, I can't ask for the metadata on the bind, because remember, I have to return to be able to start receiving data.
Oh, okay.
Unless I do some lower level stuff on the bind to just, because on this bind and that bind, I can, again, it's all about how low level we want to go. Because the go routines for the regular send and receive are not happening just yet. And these receives, I don't particularly, yeah, I just don't. It would be nice if we could do the metadata here. Because then when I get into this read, I'm just getting sort of the raw data.
Yeah, you're not worrying about metadata or
I'm
anything.
not, right? And so one way we could potentially do that is I have the connection here, right? I can write on that connection any bytes I want. So
Okay.
instead of hello, let's just even say it was that silly, right?
Yep.
So come back here for a second. I get a connection. For now, I say hello.
Connection, the server. Okay. Server rights. Hello.
And let's say I could do all of that in the bind, right?
Okay. So on the client receiving that hello, then send the metadata, and then the server says,
Let's just say we did that, right? Some sort of handshake.
yeah.
So we could hard code that right now. I could say, send this.
Mm-hmm.
Then on the client connection, con dot read, right? I'm expecting a certain number of bytes. I don't know what this is just yet, right?
Yeah.
We can define, just while I'm here for a second, some sort of again, it's variable length, right? This is where
It could be changing. Yeah.
leveraging like readers and these buff readers and writers help tremendously, because now we can just wait for the carriage return line feed on that, right?
Mm.
Where this is just read raw bytes. The standard library is already done, and I want to use the raw stuff here.
Yeah.
But let's say we went ahead and we did a buff IO just for this metadata for a second. New reader, where we're passing in the client connection, right? So now I got a buff IO. I have a new reader. Now I can say buff reader dot read line. Now I'm waiting for, say, some JSON to come in, whatever that JSON's going to be, right? That's the line.
Okay.
What was the other stuff there? Some is prefix. I don't remember. Or line. We just do that. And then now that I got the line, right, I've got my metadata. Let's define the type for this metadata. Type, metadata, structure. We'll clean all this stuff in a minute. But what did we say? File name.
File name, file size.
File name. Oh, yeah. Making a mess of this, man.
There we go.
Size. In fact, like even file name is the wrong name, but size. And we know it's going to be a 16 byte. And then what was the other thing we said?
Checksum.
Let's not worry about checksum right now. So there's some metadata, right?
Okay.
Okay. And so we know that that's going to represent that. So we can do var metadata, JSON on Marshall that.
Why is that not like form?
Because something is still off,
Oh,
and that's
okay.
fine, right? Because I've been hacking down here, so that's fine. I'm actually glad you saw that, because that's interesting. But we'll get there. Okay, so now I have the metadata, right? So I do the send. I wait here for the response. We're going to just talk in the bind. I'll get the metadata. Now, this gets complicated, actually, because where are we going to store the metadata for this single sort of connection, right, that we're establishing? So let's just do this for now, since it's a one-time sort of run, right? Since it's a one-time run, we can hack this out, right?
Okay.
Which now would mean that I got to use pointer semantics for this function, because I want to say that star, which is this MD equals MD, right? Oh, H, sorry, I should do that. Call it H. So H dot MD equals MD. In other words,
Hmm.
this is bad. This is going to work for our just initial run once
Yeah.
sort of scenario, right? We'll deal with the more complexity later. But the idea here is that I'll send to low, I'll wait for some JSON, which is the metadata, and then I'll save it in this thing here. Now, ideally, I don't want to really be using. I could be using pointer semantics. This represents an API more than anything else, right? That's the
Yeah.
rule. So I'll use that for this. That's fine. Depending on if I need that H there or not, I don't know yet. But this would go, okay, boom, 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 boom. Now, at that point, I'll return, and now I'll be waiting for raw data to be coming in, right?
Okay.
And the idea is I don't want to use any special functionality here, okay? I want to do this by hand, right? I want to see the lower level sort of aspects of this. So what that now means is, essentially, is we got to end up in some sort of loop. And we're going to have some sort of buffer.
Okay.
In fact, the buffer, my guess is a slice of bytes, okay, with no length. And I think what we could do is h dot. Now, that was the full file size, okay? That was the
Okay.
full file size. But what we have to actually do for this buffer is read. So before we do this, let's do it this way. That would be too big, right? Like, we should have a buffer of a certain size so we're not creating a lot of allocations. I
Okay.
don't know what this looks like yet, but let me just do this for now because I don't know enough. I do know the following. I do know that the first 2 bytes that are coming in is the length.
Okay.
That I know.
And why is it 2 bytes
Because that's
specifically?
what we've decided, because we don't need more than 2 bytes to hold 32,000.
Okay.
Right? Or this is, right? I don't need more than 2 bytes to hold this number.
Got it.
And we'll never use more than that number. So that means that if I do client.read, oh no, client.con, again, we're going really low level here, right? .read, it reads data from the connection. Now, my guess here then is I should be able to create a slice of 2 bytes. I've never done this before, so.
Byte 2.
And give it this, oops, sorry. Give it a L here. And this could fail, obviously, and I don't know why it's trying to help me. N would be nice to sort of record, though. And this we wouldn't have to do because it should already put it in here. And just for now, it would be nice to just print out N. Okay. I might have to turn off the AI because it's
Yeah, it's wanting to do the.
it's really getting in my way right now. So I'm just going to disable the AI, dude. It's in my way for what I want to do. Sometimes that happens. So look, I want to use a raw level read. Read reads data from the connection. Read can be made to timeout or return an error and fix C set deadline. I get to that complexity right now. But my guess is that this read, which is implementing an interface, what's right, was already sort of provided to us. I'm guessing it's going to wait until those 2 bytes are read. That's going to be my guess.
Okay.
And then it's going to tell me the 2 bytes were read. Okay. So now I've got the 2 bytes. I've got to convert the 2 bytes into an integer value, right?
Yeah.
Okay. So I have this here. and go, how do I take a 2-byte slice and convert that into an integer? Off the top of my head, I don't remember. We should start a new thread for that. And it's going to be, the support's going to be there. I just don't remember.
Yeah.
I might as well look it up here. Big Edian. Okay, so
Oh,
this
I've never
always
seen
makes me laugh.
big
Yes.
Indian.
Okay, so at a very low level,
Mhm.
numbers have to be stored in memory.
Yeah.
There are two formats. There's big Edian and little Edian. And like the Windows operating system uses one and like the rest of the world uses the other.
Okay.
And it has to do with the order of the bytes.
Oh.
Okay. So since we're writing the protocol, we get to choose which Edian we're using. So when we stuff the 2 bytes in there, we have to decide we want to use little or big. As long as we're using little or big on both sides,
Then we're
it's
good.
not going to matter. But all that being said, it's funny this came up. It's a good way of showing this. Here, let's see what this looks like. So given this number, okay, 1, 2, 3, 4, 5, 6, 7, 8, which is a 4-byte number. If we're doing big Edian, you see how it preserves the left to right notation in memory.
Yeah.
Little Edian does it in reverse.
Backwards. Okay.
Okay, so it's about the order that you store that in. Now, what gets interesting is again, we control it, so we can choose one over the other. But like which operating system uses and Linux, right? Use the little Indian little. So you see what it is like.
Oh, okay.
Operating systems have to choose one of these formats for writing stuff in memory, and you can see Windows and most Linux and ARM is using little, right? But there's other architectures that sort of leaned towards big. So we should just use little.
Got it.
Right?
Okay.
Like it doesn't matter. But now you
Huh.
sort of have an idea of that we're going to be writing numbers in memory this way.
Yeah. Okay.
Okay. It's just, right? These little things don't
Yeah,
come
that's
up.
yeah.
Surprised this didn't come up during your computer science.
I'm sure it
degree.
did. I'm sure it did at some point.
Okay. So
interesting. Huh.
So it looks like what we can do is something like that. Okay. And that gives us the value that we're looking for. If we code all this right,
Yeah.
that's the value. So that's the amount of okay, that's the amount of data we're now expecting before we can leave read.
Okay.
Whatever that is, whatever that number is, that's what we're sort of now. In fact, I don't even need this to be in the for loop because the for loop can now happen here. Right? The idea is when we first enter read, we should be on 2 bytes that tell us the length.
Okay.
Every time we enter read, we should be on the 2 bytes
right there. Yeah.
that enter length. So we're going to get the length, and now we're going to try to get all this data.
Got it.
Now,
okay.
Again, I'm going to show you how complicated this can get. Okay, because we're trying to do it in the raw. Are you ready?
Yeah.
We have to pick a size of data that we want to wait for.
Okay, just any
small number, just so it's not right. So let's say we're gonna keep a small number, 1024, just to right, which would be a lot of call. Let's do 4096, just to make it a little more reasonable, right? So 4096. That's what we're going to do. So then what does that mean? It means that we're going to be here trying to read 4096 values at a time.
Okay.
Right? And we're going to know how many that we read. And then what we've got to do is keep a counter. Let's just say that we're going to keep a counter for now. I'm really hacking here until we get enough code where I can start cleaning it up.
Yeah.
Okay. And then count plus equal n. That's going to tell us how many bytes.
Yeah.
And then we've got to ask if count is greater than or equals to val, we got all the data.
Oh, okay. Yeah.
But there's still a problem. We could have more. We could have bytes that are already part of the next sort of length transmission.
Oh.
We can only return the data that we have for this particular length, right? Because we were told, I'm sending you this. Once we get all that data, we want to send it for processing.
Yeah.
We could have more. So a couple things here, right? So
Okay.
what do we want to return in this case? What we want to return also, I should say this too. We've read we've read the 4,000 bytes, right?
Yeah.
But that's just 4 of some number, all right? So we're going to have to store the data that we're managing right now sort of here as well.
Okay.
Just so there's, we have state.
Yeah.
This is what all that buffer IO stuff, right? It's doing all of this for you in some sort of type. Okay.
Okay.
So and even that probably this should be this, right? But we don't do a construction there. So we'll just be inefficient for a long minute. Actually, no, we can just do this here, couldn't we? Say h dot data equals this for now.
Yep.
And again, it's a new slice. We could be smarter about it, and we will later, but that's fine. And then what we're going to do here is we're going to get our count. H dot data will equal append H dot data. And then we have our data, right? Now, again, we could be smarter than this too, because this is a slice.
Yeah.
We're going to be smarter than that. We can give it pointers into the slice where we don't have to be making copies.
Yeah.
We just have to move. But these are all little things we'll do later.
Yeah, later.
Right?
Once
There's
it's working.
Large amount of inefficiency here. But once you get this working, this can be, because of the power of slices, this can be so much more efficient. Okay?
Okay.
But I don't care about efficiency right now. I just want to see something work, right?
Yeah.
So let me just add some notes here, right? Just create a now actually create a buffer. This buffer might be wrong because this is actually bad what I'm doing here. Can't do this. Can't do this because the buffer has to I can't do this because we're going to have some leftover bytes that we just can't mess with. This has to be sort of created once, and it has to store any leftover bytes that we had for the next sort of call is the real problem.
Why is there that overlap?
Because it's TCP, bro. I mean, it's just sending you.
Oh, so
you think we're waiting for an acknowledgement? Now, if we wanted to really slow this thing down, after we send that, we can wait for an acknowledgement, and then you have no leftover bytes. But that's going to be slow as hell.
Now
you just want to be going chunk, 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 length, chunk, length, chunk, length, chunk, go, 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 right?
Yeah. Okay.
Now, ideally, we could simplify this actually. And maybe I'm making this more complicated. Maybe that is the total length.
The total length of everything.
Yeah.
Okay.
Instead of a length of the next chunk. See,
Okay.
if we do the length of the next chunk, we save a lot of memory.
Okay.
See, that's why I want to do it this way. You're saving memory because you're processing and writing 65 as opposed to here's 10 meg.
Yeah, here's
You
10
don't want to
megabytes
do
at
that,
once.
right?
Yeah.
So this is about a buffer of, let's go back to this for a second. So we're going to have a file size, but we're also going to have like a chunk size that we're going to manage, right?
Okay. Yeah.
And this is where I said like 1024 times, say, 64. Okay. So let's do this for a second. What this read is going to do is just wait for a potential chunk of data.
Okay.
But that chunk is going to be told, we're going to be told what that is. I'm trying to be a little efficient already by pre-allocating some memory here,
Yeah.
right? But let's completely not be efficient for a minute. Let's just be completely not efficient. I can do this, okay?
Yeah, you're not allocating.
Let's not be efficient for a second. So we need a buffer for this chunk, okay? Then let's read the amount of data expected for this chunk. Let's just be really inefficient right now. There's our value, right? So func.println expecting the chunk size of val, right?
Yeah.
Okay. Now, loop until we get all the bytes for this chunk. And we're going to do it at 4,000 bytes at a time.
Okay.
Okay. We could do it. We could make this, let's say, the size of the chunk, but that doesn't help us either because we might want in this loop to be able to get out early, to be able to do things, right? Because we'll be sort of blocked until so maybe all that happens. But again, it's all about memory at this point and efficiency. There's a balance. So if we only read 4,000 bytes at a time, yeah, it could be potentially a tiny bit slower, but how much memory do I have to store at any given time? Right, I can reuse that 4,000, plus I'm only storing whatever the chunk is. We can play with some of this. So now I keep track of, now, do I really need this? The answer to me now would be no, because if I store everything in this chunk, then it's the length of the chunk, right? If that's greater or equal to, oh, now that's an N16, right? No, that's fine. That's fine. It's fine. So let's call this uval. And just to make our code a little simpler, val. Again, we'll clean all this up, right?
Yeah. Let's convert it.
Yeah. Just, we'll clean all this up later. I don't really care. Now, it might be fun to just print this out. Func.print line, right? Received chunk. And then, right, we received the say 4,000. We're asking for 4,000. We should.
Yeah.
Now, at some point, though, we might get, and we will get 4,000 bytes, but it sort of goes over.
Okay.
So now what? We know we have all the data that we needed, but we also have more data than we need.
Yeah.
Can't return more. So if this is the case, if it's, let's say, let's make it simple. If we've got the exact amount of data in the slice, then what do we know? Let's just keep it simple for a second.
Switch case.
right? If it's case this situation, then we know we can return the chunk because it's perfect.
Yep.
The length of the chunk, perfect.
Yep.
And no error. Okay. Again, dude, there's so much. Anybody who's watching, we have a lot of code to clean up. I don't care about that right now. I just want to get something working and then look at where we can have efficiencies. Now we have another situation. If the length of the chunk is greater than val, this is the complicated one.
Yeah.
Because what that now means is we want to return chunk up to the value. Those would be those bytes.
Okay.
You're returning val and you're doing nil. See, that's what you're going to return. Well, what about all the bytes that were?
Yeah, now they're sort of left over.
I know we can't lose them.
Yeah.
Right? Like that can't be lost. So this is where, right, we have some sort of buffer overflow. So let's say that we did this. Okay.
Okay.
We have some buffer overflow there. So then maybe what we can do is say, fine, buff will equal chunk. And remember, it's greater than val. So, h dot buff.
No.
All right. And let's get rid of this for a second. So you see here, what I'm going to do is keep all the bytes that we had
beyond
that and then return that. Now, what does that mean, though? We come back here.
They need to end up somewhere.
Well, now things get a little more interesting here. Because we already have sort of buff data in there, right?
Yeah.
And we assumed that every time we called read, we would end up with, right? We wouldn't come in here unless the next read is a particular.
Yeah.
But there's no guarantee in these things unless you're doing. See how complicated this thing starts to get.
And but then we're also we're assuming that the first 2 bytes are always going to be like that.
But it may not now. Those
Like,
two
but it may
bytes,
not now.
those 2 bytes that we need might be.
They might
buff.
be, yeah.
Yeah. And so this gets interesting because I only want to do the read if we sort of need to do the read. And I know that I'm now looking for length. Now, that being said, however, if I've got any data in the buffer, let's think about this for a second.
Okay.
Now, what if one case we didn't handle is what if the case of the length of chunk is less than val? I mean, technically that should never happen, right?
That wouldn't be like the end of the file? Like if there's
no, because val will be a small number. We should have it, right?
Okay, val would.
Now, I don't know what to do here.
Val would adjust.
So I'm just going to go why. Again, it's our little hack program, okay? Why? So here's my thing. Either we got the exact number or we have some sort of buffer, but we've got to be able to process the buffer before we do any more sort of reads. See what I'm saying?
Yeah.
So we can't assume anything at this low. This is all really low level stuff, right?
Yeah.
So we're reading raw bytes and then we're sort of processing raw bytes. So what might be bad here, what we might have to do is maybe always just read into the buffer and then process sort of the buffer where it's at. Are we even using chunk? Where are we using chunk? We're using chunk there, right?
Down there in the
Because now what's happening here is we come back into this read loop because we finished processing these bytes.
yeah.
We know that was a set of bytes to just sort of write to disk, and now we want the next sort of set of bytes. And the thing is, we come back here, but there's a good chance that we already have a length. So maybe we do this. If h dot buff, right? If the length of h dot buff is greater than 2, what do we know? We know that the length bytes that we need are already in there, aren't they?
Okay.
They're already there, right?
Yeah.
This code is really bad right now. We're going to fix it. So I would argue then that what we need to do here is get our length. That should be the length.
If that's in the okay.
And we do that. Now, once we do that, we need to take those bytes sort of out of the buffer. But I don't like what I'm doing here because this is going to be a mess. What my brain says is that what we want to do is probably work everything into that buffer.
Okay.
In other words, process the buffer itself at all times. Don't try to do some reads and then not. So either it's in the buffer or it's not in the buffer.
Okay.
Okay. So what that tells me is I think we need a different strategy. Let's call this the buffer.
Okay.
Okay. So maybe what we want to do is the following. Maybe read is nothing more than this code here.
Okay.
Oh, wrong place.
Yeah.
Let's say I'm going to move all this code for a minute. I'm not getting rid of it. I have it on my clipboard. And I'm going to put it in here for a long minute. Now, imagine this was all we did in read.
Okay. Getting the data, allocating to that.
We just read 4,000 bytes.
Yeah, always.
Out of the raw network. Now, we have to do this, though.
You have to have some kind of buffer
Buff
for
equals... I keep waiting, and then I realize we turned that off, right?
Yeah.
Buff dot... in fact, it could be... let's just do it. Let's do it the inefficient way right now, okay? So we're going to read 4,000 bytes, and then we're just going to append those bytes to the current buffer. Luckily, the call between read and process is serialized.
Mm-hmm.
So imagine that's all we did. Just threw data into the buffer. Okay?
Yep.
Now, what would that mean next? It means that when this gets called, we have data in the buffer of some amount.
Mm-hmm.
Okay? Now, what we need to sort of know is sort of where we are in terms of needing length, or we just have raw bytes, right? We need some sort of so what if I did length here for just a minute? And right, so that's the length we're looking for, and it's the current. I don't know what to call this yet.
Yeah.
But I track where we are as relates to the length.
Yeah.
Right? I don't know. So then what would happen here? Okay. So we now got to process this sort of buffer. So let's just start sort of from scratch here. We've got to, for sure, I think, loop again.
Okay.
And I think we have to know where we're at. So on the very first time, length is 0, current is 0, correct?
Yeah. Okay. And length and current is referring to
Where we are in this,
where we are in that chunk.
in that meta, yeah, in this chunk. So
Okay.
let's just start off first and worry about the next iteration.
Yeah.
Let's just assume that we know the first 2 bytes is going to be the length, right? So we've learned this already. We know to sort of do this. And actually, we don't even need this, right?
Yeah. But
Okay. So this gets us, okay. The number, I haven't been looking. Oh, nobody's been sending messages. Number of bytes to wait for, right? This is the number of bytes to wait for. Okay, we now know how many bytes we're waiting for. Now, the problem is that we may not, now all these bytes that we're going to get now, we want to write to disk. Agreed?
Yep.
Okay, so let's say we did this next for a second. Oh, it's not a read. We're in the buff.
Oh.
We're in the buff, right?
Yeah.
So what that would tell me then is if we wanted to just be, again, let's say I just did this for now. I don't know enough yet. I want to move the index of the buffer over 2, right? So
Okay.
now we're looking at the next.
So we're looking at the data, not the length.
Yeah, now I'm at the data,
Yeah.
right? And we know, because we're coding this, that we probably need to make this even larger if we wanted to be more efficient, because we wouldn't get the full, well, we know we're not going to get the full data anyway, but that's fine. So now I've moved that over. The problem is I don't know, I need to only write the length. So I need to know how much we've written at this point. Correct? I know what the length is. Okay. I can say h dot length. That's how much data we're now expecting.
Yep.
Related to this particular chunk. I don't know if I have that length at this point. And I need to know how much I've written. Right? So maybe this is,
that's one
written, right? That's how much I've written on this next sort of length here. So what do we do here? I have a length for this buffer. Okay. And I know how much I've written. I've written 0 at this point.
Yep.
So what do I do, dude? And we'll just do printfs for the right, which is fine. But I need to know, can I write this entire buffer to disk and it's all data? Or am I going to be, is there length now back in this sort of thing, right? So let's just think about that situation for a second. So on a case, the length of the buff, right? That's how many bytes we have.
Yep.
What do we know again? We know that we have this sort of chunk, right? That's the length, the chunk. We know how much we've written already.
Yep.
We have a buffer now. Maybe we need to do some math here, right? How much of that buffer do we want to write to disk is, I think, the bigger question. Because if we do that, this simplifies. Oh, dude, I think we can simplify this.
By deciding how much of the buffer to write.
I think what we could do is make sure that every time we call process, we have length in the beginning of this buffer. That's what we're going to do.
Length in the beginning of the buffer. And that length is for the entirety of the buffer, not necessarily starting from 2 or...
If we can make sure that every time we get into process, okay, because we've read 4 bytes. Well, what are we doing here again? I'm reading 4,000 bytes, I'm appending and I'm returning it. Yeah, I can't assume that, right? I can't assume that. This is hard shit, right?
Yeah, it's
so
super.
This is why everybody's doing networking protocols with delimiters. So you're just streaming bytes and you're looking for the delimiter and then you're going.
And then you're done.
Yeah. I'm trying to do this by looking at length and stuff.
Yeah, count.
So all this is doing now is 4,000 bytes of a buffer. I can't assume that we've got a length at the beginning of it.
Okay.
But I can make sure that that if we ever do have a length, it's going to be in the beginning. Could guarantee that. Okay. I'm just going to need some sort of flags here to deal with that situation. So let's go back to this loop. We'll nail this. We'll figure it out. So there's a couple things now, right? Let's just put it here. I'm back here. Okay, so we need to know if we expect to have a length at the beginning of the buffer or not. Now let's say there's a way to do that. Okay, let's just say, right, that there's a way to do that. I don't know yet, but let's just say there's a way to do that. Okay. Again, I really want to set this, let's just say is not length right now, because I have to set it in the negative because I don't have a, right. I basically need this new for everything I want to do. I kind of need a new function that we're going to have to use because there's some state here that I have to deal with, right? Return. And I'm expecting is length to be true, right? To sort of start out with.
Yeah.
Everything else right now can be there, and eventually we'll yeah. All right. So let's just do that for a second. So if h dot is length is true, that's nice, because then we get to do all of this right out of the box, right?
Yeah, okay. Its length and then the buffer.
So if we're expecting that the length is at the beginning of the buffer, then we can do that. If not, then we know we just got pure data that we sort of have to read. Okay? But we can't just blindly read all the data because, again, there could be some more length in there. We want to read what we have up to the length. So we have to know what we've sort of written already. And I need the length of the data as well. So we store the length. We set the buffer. And now we ask some basic questions. Okay, is the current length of the buffer, let's say, is it less than the length, but is that plus what we've written, right? So I need to know what I've written. This is where it gets complicated, right? Yeah. What we need to know is the following. Let's say I've in this case, I've written 0 bytes.
Yeah.
Let's say the length is for this 4096 bytes.
Okay.
And let's say the buffer right now is at 1024. So what does that tell you? Tells you to write the full 1024.
Yeah.
Why? Because we've written 0. We want to write 4096. And that's going to then go back into that, right?
Yeah. Okay. But
So let's say we did that first. Okay, let's say on the next loop, what do we know? We've now written 1024. The length is still that. And the next buffer, let's say, is 512. What do we know?
But we've written 1024, not 4096?
No, that's all that came in.
Oh, because we're talking buffer specifically. So we write the 1024, and then on the next one we have 512. So now on the next one it'll be 512 plus
But we write the whole
1024.
thing. Why? Because length minus written, right? Length minus written,
It still leaves.
it's still greater than,
Yeah.
right? So it's like, this is total, right? This is like the total. It's more like the total. Like, this is the chunk size, really. This is the chunk length we're waiting for, right? So when I say written and I say chunk length, all right, but this is the length here. So I'm going to change this to the chunk length. This is what works. This is the number of bytes we're expecting. Okay. So what do we always know? If I take the chunk length,
Yeah.
minus the bytes written,
Okay.
okay, if that value, okay, if that value, or if this value, which is the buff, the length of the length of the buff is less than or equal to that, then we know the following. Right? Percent D bytes to disk. And that's going to be length buff, right? So we wrote those to disk. Now what do? We've got to take them out of our buffer. Again, there's more efficient ways to do this.
Okay.
So that's our new buffer. Now what do we know about? Now, bytes written plus equals that, right? So we've written those bytes to disk. We've gotten rid of them out of our buffer. We can be much more efficient with that with an index or something, but don't worry about that right now. And then we increase written. Now, this is a case where we've got less than.
Yeah, if it's
right,
greater than.
Well, equal might be a separate scenario too.
Equal to. But then that wouldn't be less than or equal to, it would just be less than.
Yeah, I think this is just less than, right? Now, let's do equals. Because equals gets interesting, right? If by some miracle, this exactly matches
the chunk length minus.
So if the chunk length minus the bytes written equals this entire buffer, then we know we've written all the bytes for this. See? And this is where I would want to say is length is true. We now know the next byte in the buffer has to be length because you've just finished writing. But we have another scenario.
Yeah, where if the length of buffer is greater than
Yeah,
the chunk length minus the written.
which is going to be the case every single time. If this is greater than, then we know we've got more bytes in the buffer than we need. So write bytes to disk 1, write bytes to disk 2.
Oh.
So how do we do this? It's not writing that length anymore. We've got to do the math on length. So the length is going to be what?
The written, no. Hold on.
How many bytes do we want to take from this? We just need the difference.
Yeah, you want the difference of what's in the buffer versus the chunk length, right?
So if we do that, that's our difference, right? That's how many bytes we needed to complete the process. So we're just going to write that number of bytes, right? We're going to take those number of bytes out. And now written can be, written should be 0 at this point because we're done. And his length is, see?
So the buffer is greater than the difference of those two.
There's so many ways to make this more efficient, but we just got to get a version of this working.
I just don't know why, like, the numbers isn't computing for me right now.
This stuff's not easy, bro.
Like, I'm trying to picture the...
So this is the idea, right? We start reading 4,000 bytes at a time.
Yeah.
We just keep putting that into a buffer. More efficient way to do that too. And then we sort of process this. Now, we can test this little function before trying to get, before we try to actually use this.
Okay.
You know, we should probably do that. Test this sort of logic out. All we need is a stream of data. All we need is a buffer with a shitload of sort of data in there.
Yeah, and see if it actually breaks it up.
We're streaming it properly, right? Because we could do it with one big sort of buffer to start, and then we can sort of feed it, call it with chunks of data at a time, which is probably the best thing to do. So let's do this for a minute. Function main. And let's take this little piece of code we have here, okay? And I'll wrap it in a function. Whatever. And what we'll do is when we call Kevin, we'll call it with a buffer, which is a slice of bytes. Okay. And it can return an error. And what we'll also do is just create some variables, is length. And we can even set that to false, right? And the idea is we'll process this buffer that we pass in.
Okay. Yeah.
All right. We'll need the chunk length, which we're setting here anyway, and we'll just create a variable for that. Fine.
And then we need the buff, which we...
And we need the number of bytes written, which can be an int right now. That's fine.
Oh, okay, yeah. And we're providing buffer because...
Oh, why didn't that work? D. Oh, there we go. This can just be buff. And it's going to be chunk length. And we'll find some efficient ways to do this, right?
Yeah.
Because this is the core of everything that we want to do, right?
Yeah, this...
And what we'll do is not just say write to disk, which, by the way, this should have been F that we didn't catch.
The is length, is that getting whether, like, what is...
We're trying to figure out that we're at the beginning of the 2-byte marker.
Okay.
But what I'm also going to do then is just for now, and we'll clean up this output in a minute. That's what we wanted to write to disk, right? And, oh, yeah, that's fine.
Okay.
And then that's what we wanted to write to disk. And this is what we want to write to disk. And we'll just see that being written.
Yeah.
We'll just start real simple, right? And then let's create some data. That will be a slice of bytes. And actually, we can do a slice of bytes. And we'll sort of stream this in the way we need to. Now, the hard part is going to be, actually, we can do this. We're just going to be using English anyway. So, like, I shouldn't get any compiler errors doing this. Oh, I need another. I need another this. Okay, so fine. Now, let's go and look for, let's do a couple things. It's going to be hard to get the length in there off the top of my head, but we'll figure it out.
Okay.
I just need some basic sentences. All right. 10 simple sentences. Just give me some 10 simple sentences. All right. Like even this is fine, right? Because the numbers you got to be kidding me. You're not letting
You can't copy paste.
I don't think I could, that makes me want to just like do an inspect and
steal it.
And steal stuff, dude. Like, why are you doing that to me? Like, it was so unnecessary to try to pretend that you could stop me. I mean, that was cute. All right. Let's see here. What we could do is read this in. So let's start with this. Okay, I can read this in, right? This is the raw data. Oh, here's the data. And then I could do a loop for D range data. Okay, and I would have each one of these sentences, but in order to produce this, I need to put the length of that first, right? So it could be the length of data.
Okay.
And then I have to write, I need it in 2 bytes, right?
The length of D.
So
okay, because it's going to go.
Yeah, what I essentially want to do is this, right? I want to create a buffer, which would be a slice of bytes, right? And I could argue that again, I don't have to be super efficient right now. I can say buff equals, well, D is the string, right? So I could do this, but I need to put the 2 byte, the length in there, right? D is a slice of, oh, oops. Now that I got strings here,
Oh, it's
I
just a
changed the
slice.
data. Yeah,
Okay.
I changed the data. So, but I need to put the 2 bytes of that length, right? I need this to be a 16-byte integer. So I could do the following, probably to make this. I essentially need to turn that into the 2 bytes, which I bet you with the little Edian, where did we have
Right
that
there.
binary? Let's take a look at this for a second. Man, it's been so long since I did anything like this. So put, yeah, that's what we need right there, bro. Okay.
Stores V into B0. Oh, okay.
Yeah, that's what we need. So I do a uint16 on L. It will fit. And then I can do a var B and, oh, that has to be already 2 bytes of length. So, or it will blow up, right? So I
Okay.
do that. Technically, yeah, I can do that. But now I need to do this. So,
But you need to put that into
yeah, I think if I do this, we'll be fine. I do this, and then I say, again, very inefficient.
append. Yeah.
Very inefficient. But
So the more efficient way is just using pointer.
just hold on. No, a more efficient way is trying to pre-allocate some memory and not doing these appends and little extra copies.
Yeah.
But
Okay.
I don't care about that right now. Why is my editor like?
Yeah, it's like highlighting the.
What is wrong? It's not supposed to be that. So
No.
what is it supposed to be? Oh, I see.
Oh, did it? It had like a. Oh, okay.
That's fair. So look, for each item, we set we get the 2 byte value.
Yeah.
We append that to the data. We call Kevin.
Yeah.
Length can start out as true for our purposes, right? We should be able to get the length. Let's from dot print line. Oops, hitting the wrong keys. Length. That alone will be sort of interesting, won't it?
Yeah.
Like we get the length right. And we could, I'm sure there can, oh, it doesn't fail. Print line, calling. The output's going to be a mess until we know more. But,
Yeah.
Calling Kevin, right? That's your length. And then new line, right? That's our new line with some length. You should be able to say we're writing that number to disk. Now, in the case that I'm doing here, everything is of the exact sort of size, right? So we should be seeing 2 the entire time. Let's just see what happens. I'm like super curious how bad this thing blows up, right?
I just want to see like the numbers, how they work out.
It's gonna be ugly, bro. Yeah,
Panic.
man. Let's get some blowing it up here. So calling Kevin with 10 bytes. Let's at least see that. That makes sense. Write 10 bytes to disk. Start new line 10. That's fair, right? So we got the 10 right.
Yeah.
Right? That worked. I told you that we would only be in here. So we were in there. I just did some bad slicing work because we
were in the...
we did this, and then I went to... This is all mess here.
2. Okay, so we were in the equal.
Oh, you see, this was dumb. This line of code was dumb. Because what we really wanted to write in this case was... Let me think. Well, it equaled, didn't it? So
it did equal.
We essentially want to do that. We want to print the whole thing, and then the length of our buff equaled that, so it was a match, right? And that was what, 10 bytes?
10.
So ideally, at that point, the entire buffer gets displayed.
And then buff is buffer.
Ideally, all that does go away because we're getting rid of it.
Yeah, why?
But I think that's also now going to blow up. I got to think about that. So 45, 30. So far, I'm happy. That was good.
Yeah, and then the slice bounds from 2 to the length. It's like from...
That's not what blew up. This is what blew up.
Oh, okay.
So what?
But it should be 0.
Oh, we never broke out of the loop. At this point, we're done.
Oh,
right?
because it's...
Yeah. At this point, we're sort of done. Like you break. I got to return, let's say. Because there's nothing left in the buffer, right? And now this is going to complain that it's never used at this point. We're going to have to play with some bigger buffers here. But
okay.
The idea is that right now we're making it simple. I'm giving you this, you process this. I'm giving you this, you process this, right?
Yeah.
And so in this scenario here,
oh, there we go.
Right? Which, okay, whatever. This is not going to be reality.
Mm-hmm.
But I'm happy. She's exercising every morning. We're doing that. The reality is going to be more like a bigger buffer with length in it. So let's do this. Let's do a final buffer here. Buff. Let's do this instead. The L buff is this. Bar buff slice byte. This is going to be much more realistic. Buff equals append L buff. Two bytes. We're not going to call Kevin here.
Okay.
Call Kevin here. So I'm going to take all of this and assemble it into a single stream.
Got it. Yeah.
Okay. And then what's going to happen is we're going to stay in this loop until one of two situations happen. If the buff length is less than, then we have to loop again. But if the buff length is greater than, At some point, the length of the buffer is going to be processed. And maybe that's what we're missing here, right?
Okay.
Because I think what we're missing here is that scenario. We're doing this wrong. That's why I wanted to do this. Let me put this back for a second. At the top of the loop, we need to ask if the length of the buff is 0,
Okay.
return, right? Because we've processed this buffer completely.
Yeah, there's nothing left in it.
Okay.
So we have everything.
We've processed it completely. We do that, and now we just say, because once we do this, the buffer should be 0, right? So let's try the following now. I have no idea what's going to happen. But printing buff. Here we're printing. In this case, the length of the buffer is less than. So we're going to be printing the entire buff as well, right? It's less than. And then we're getting rid of that length at that point from the buff. I mean, in this case, we're writing the entire buffer, right?
Yeah, because it's less. Yeah.
I mean, at that point, this is what you have, right? So we should be able to do it this way without any problems. I should be able to.
Why was it complaining there?
Because of that.
Oh.
I should be able to cut that out, and it should be 0, like unless my math is wrong. Anyway, let's see what happens. Oh. Okay.
Now
calling
it's disk 3.
Where did I write calling Kevin? Okay, that's fine. That's sort of silly. 10, 28, 21, whatever. So disk 3 was that, and that should have been. Let's do this. So we have it 2. I'm going to have the length, and then I'm going to have D, right? Let's do it. It didn't blow up, and that's good. So this is everything in the stream. Now, the way we wrote this is we're trying to do lengths properly. So we said 10. I don't see I'm happy. I see she exercises every morning. So we already sort of screwed up because I didn't really get
that first.
I'm happy, right?
Yeah.
Okay. But we did end up on disk 3, where the buffer is greater than the chunk length, which should have been 10, okay, minus written, which is fine. So chunk length 10 minus written, diff is 10. I started printing 10 in.
Oh.
I got this wrong. I want to do this. From the beginning, do that, and then subtract. Let's try that. Okay. So I got I'm happy. Then we got 28. She exercised. His dog barks loudly. See, that's all working. And then we got to 2, which is those kids don't speak English. And then we were done because we didn't have any more bytes.
So because it was going to disk.
Right.
3.
So this logic is working, right? Based on a stream that's coming in with bytes and strings. The only case we haven't tested is this. And we can test that too. What we can do is, which would be interesting actually, switch this now to okay, how could we do it this way? Imagine I did it this way for a second.
Okay. Oh.
Oh, I don't have a buff, so
Yeah.
okay. Again, I don't care about efficiency right now, dude. I
Yeah.
just care about. Okay, so look. I add the 2. I send that in. What would happen? We'd get the length,
Yeah.
but now in our case, buff is 0, isn't it?
And oh, I like the buff 0.
It could be 0
Okay.
because those are the 2 bytes. That's what I'm doing now. I'm forcing in a length.
Mm-hmm.
Then I'm forcing in some data.
Okay.
In that case, I'm trying to get on this scenario here, right? I'm trying to get where we just got 2 bytes in and we're going to make this more sophisticated as we go.
Okay.
But at this point now, you're going to get 2 bytes and then you're going to get the rest of the data.
Right after. Okay.
So is length will still be false at that point. Oh, you know we didn't do.
Oh, reset.
Once I have it, then it's false because I have it, right? That's where it needs to be done.
Okay, because that
On false needs
that
to be
buff we're
set
getting
there. If
has
not, now it's true here.
that buff that we're getting has a length in the beginning.
We never set it to false, did we?
It got no, it got set.
That's because everything is so perfectly even. We're going to get this to a point where things are not even.
It's not even.
But once I have the length is false, right? We're not looking for length anymore. We're looking for data. So if I run this, I don't like this. It has to be a little bit more random. But
1 1 1 1 1.
no, so things are off big time now, right?
New line 11.
So I didn't get everything here, right? So this is bad.
Okay.
Oh, calling Kevin, I'm happy. Where do we call new
10.
line? Okay, a new line coming in, right? 10 bytes. We said write those bytes to disk. And then that was 3.
3.
And then there's some carriage return, which I don't know where it's coming. And we didn't get the whole, we're missing 2 bytes there. So the diff is sort of off, isn't it? And then obviously we get the wrong.
Because it should have been I'm happy, not I'm
happy with the period, right?
Oh, with a period. So there's 2. Yeah.
So the diff at that point was sort of off, right? We know that the diff was write bytes to disk 3. Oh, write 10 bytes to disk 3. So the diff was correct. It was 10. And we said start at buff. Somehow, my guess is we still had length in the. I wonder if we still had. We may have still had the length in the buffer. It didn't get parsed out. Because buff equals, yeah, we came back. Oh, okay. The length was still in the buffer.
The length was still in the buffer
Yeah,
in the
because
front, which is
this
why
function really should be returning. For this code to work, we need to do this.
the new.
This needs to be like this, man. let's forget about errors for a minute.
That would make sense. So it pushed everything over, and that's why the last two got
Yeah.
cut.
So
Okay.
we can return nil here and here. But what's going to happen is, yeah, we don't return until the buffer is 0, right? All right, let's just run it again now.
Disk 2 now.
Yeah, we're seeing all 2s.
Yeah.
Okay. Because we're coming in now and it's always equal again.
Mm-hmm.
Because the length of the buffer, we already had the length, and then it's the same. So this is what we're going to have to do now. We're going to have to get sort of creative. And this is where we're going to, we got to write the two bytes in here, okay? But this is where we're going to get sort of creative. What we can do is pick sort of a random number and call Kevin with those. Now, the way this needs to work, though, is that at some point, right, at some point we've exhausted this buffer.
Yeah.
Right? Which is fine, because we never return until we process the entire buffer. Which probably means we didn't have to return Kevin out. We can just assume the buffer is nil. But just for this alone, we don't always want to send all the bytes in. We want to sometimes
Like randomize
the
it?
maximum number is 10, right? So what if we did rand, I think it's math.rand or rand dot int n, okay, giving it a number, say 8, all right, some value v. That should pick a number anywhere between 0 and, let's say, 0 and 10, not including 10.
So yeah, 0 and 9.
V equals 0, then make v equal 1. Okay?
Okay, yeah.
Now, what that's going to tell me is that we're going to send this in twice. We're going to first send v number of bytes, and then the remainder.
Okay.
So v equals 10, then the remainder is going to be the length of d minus v. Okay? And then we're going to do the following. We're going to send in d through v. And actually, I don't even need the remainder. I just need v. Now watch what happens. All right.
D.
And I don't think I need,
from V.
and I don't need this because we never return an empty, like, I just don't need that. All right.
Okay. So that should throw off the count a little bit.
But buff has to start fresh every time is the real problem here. So let's just do it again. It just makes it easier if I return for now. Because we recreate buff here. It's just turning a nil for me. So we're going to send in, now this will change every time, right? We send in some random number of bytes.
Yep.
Then we send in the rest.
Okay, yeah.
And this is going to be much more sort of realistic to what happens when we're running this on the network.
1, 1,
so
3.
New line 10. Write 3 bytes to disk, right?
3 bytes.
Now write 7 bytes to disk.
Yeah.
And you can see that it handled the partial sort of shit. And then this is what the client sent. Okay. We got 9, and then we got the, oh, no, something
Yeah.
bad happened. That's fine.
Something bad happened.
Something bad happened.
3.
But that's okay. So it was all disk 1 that was fine. This time we sent in 9. It's almost like we didn't send the whole thing on the second call. Let's double check that code. See how it says just write 10 bytes?
Yeah.
Okay. Let's double check what we did here.
Oh shoot, I do have that 1 p.m.
Okay. We're going to finish up. Okay. So this is what we're going to do. We're really close, right?
Yeah.
We've got some little bugs here, but we're like super close to having this little algorithm working.
Yeah.
Once this is working, we can go back and incorporate it into the networking side. But what we've got to do is continue to make this random as possible, throwing bytes in there and us processing it. And then we'll come back and make this super efficient. So
Got
we'll
it.
finish this work on Thursday to make this sort of byte streaming
So this is essentially what's all going on behind the scenes in like the buff IO stuff.
written 10,000 times better.
Got it.
Yes. But I think if we just focus on this on Thursday
Yeah.
and make this 10,000 times better, because just writing this code, we're learning more.
Yeah, about how to handle the
on how to handle it.
Mm-hmm.
I don't want to do 1 byte at a time. That's really inefficient. That's why this length is so important. So we're pulling chunks of buffers out, but we have to check lengths and stuff. So let me at least do the following for you. Have to jump off, get status. Let's add this to the project anyway. And this is our hack work for networking. And then on Thursday, we'll come back to this, get this code working.